And so what you're going to need to do is to have a computer. Hopefully you have one where we can go on Google's Colab. I think I have a link on our Moodle site. Let's go check and make sure. And then if there's any issues, I probably should have emailed you to warn you ahead of time. So I apologize that I didn't warn you that we were doing this today. I think I might have said it. Well, maybe. But anyway, yeah, there's the link. So there's a link here on our Moodle site at the bottom of the first section, the general section, Google Colab. And honestly, I'm always signed into Google. You might have to sign in. I don't know. I don't know how it works, but if you're having trouble, let me know. I'll just wait for a minute, make sure that everyone can do this. And once you are on there, all you got to do is click New Notebook. So down at the bottom, this big blue button, New Notebook, and then we'll get right to it. So I'll give you a minute, though, to make sure that everyone's in the same place. And let me know if you need me to come look over your shoulder. All right, so first things first. I had a lot of trouble with Google Colab until I discovered that I could turn off this nonsense. Now, I say that just somewhat tongue-in-cheek, but I was amazed. I got to tell you, I was so impressed with this. It's come a long way since ChatGPT, at least from a year and a half or whatever, however long ago I started playing around with this stuff. I was quite impressed, but we want to try to figure out how to do this stuff ourselves. And we could just ask the AI to write the code for us. But here's what I'd like you to do, at least for now, for me, if you humor me. So there's this giant gear in the upper right corner. When you click that, you get some settings. And the AI assistance thing here, when you click the little box that says hide generative AI features, that'll just help out. It mainly is because it was getting in the way. I wasn't so much frustrated that it was there. It's just that every time I typed something, it was trying to complete my entire, and I was like, well, I don't want to do it that way. I want to do it my way. And so it was just frustrating. So that's why I finally figured out that I could turn it off, and it just made it so much easier. Okay, so if everyone's got that, I'll just wait a minute and yell if you, well, call me over if you're stuck. This chair is on the floor. I need a bigger chair. It's going to bug me. So call me over. I don't know. I'll just assume that everyone's good. So here. So basically, what we're going to do, I'll tell you what I'm hoping to do today. We're going to code basic coding for Python just to get feel for it, and then so understand how Python works just briefly. I'm not really going to teach you Python, but just so you know the basics. Then after that, we're going to code the bisection method, the secant method, the Newton's method, and then if we have time, we'll do the bracketed methods. So we'll see. If we don't have time, then we just won't have that on the homework. And then your job, just to keep you inspired to stay with it, your job will be to experiment with those methods. That's the homework for Wednesday, is you'll be experimenting with those methods. So first off, Python, it's, I don't know what it's called. I'm not a computer scientist, but what you do is you type code. For example, I can type A equals 5, and then on the next line, I could type something like 2 times A. And then if I hit this little play button over here, it will spit out 2 times A, I think. It's going to take a minute because it has to start up the Python kernel or whatever. Oh yeah, there it is, 2 times A. So if you do that, there you go. So we can type various commands in here. We could even do something like, let's see, for, let me see, I can't remember exactly. Oh no, while, I got a while. Let's see if I can remember for. What is the syntax there? For? Just a minute. Huh. Okay, we'll do while. Okay, so here, so we have A equals 5, and we could do this. While A is less than 20, and then put a colon. So apparently I can't remember the do loop, but it's okay, because all of my code here has while loops. So this will do it. But any looping, any if-then statement, you end with a colon, and then everything is indented. So anything under here. So that's how the flow works. And once again, I'm not a computer scientist, but so I'm sure that this has a name, the way that this works. So notice that this is indented. So while a is less than 20, it will just continually do whatever is below here that is indented. So I suppose so that this doesn't keep going forever, I should say something like this. A is equal to a plus 1. I think there's a quicker way to do that, but I don't care. And then I could do something like print a squared. There. And so basically, while a is less than 20, so it'll start with a equals, well, 6, because it'll add 1 before it prints. It'll print 36, 49, 64. So that's kind of the basic structure. I'm sure everyone here has had some sort of a computer class, so you're probably familiar with this idea. So let's just see what this does. So there it is, 36, 49, and it ends when a is equal to 20. Well, technically it ends when a equals 19, because then it gets to 20 and it says, okay, I'm all done. So that's sort of the general idea behind some of the stuff that we're going to be doing. There are some packages we can bring in, but we're not going to today, that will help us with calculus and so forth. But I want to get to the actual programming of this stuff. Now, another important thing, just as whenever I teach statistics and we use Excel, it's super important for you to let me know if you're stuck in any way. So if you have any problem, let me know. We will pause. We will find out what the problem is, and then we will come back together. So let's take my notes, and we'll get this done. Okay, so I don't know how to do this with a mouse, but in order to get a new, I guess I could press this, maybe? Yeah, okay. I could do that. I use Shift-Enter. So you can either press play. So here, let's go back up here. A couple other things about the way that this notebook works is if you want to see this, to like what happens when this code is run, you can either press play like that and it does it, or if your cursor is somewhere in there, press Control-Enter and that does it. And then the last way is if you press Shift-Enter, it runs the code and moves you to a new block of code. So anyway, like I said, please do let me know if you get stuck. Okay, so before we do anything else, I should pull in the math. So from math, import star. So what this is going to do is it's going to allow us to use all of the math package, things like the sine, cosine, tangent, exponential function, pi, anything like that. So this is going to be standard practice for us. I'm sure that I'm not doing writing my code the way that a real computer scientist would write the code, but I'm going to just do the best I can. Okay, you can define functions. Notice this is define f of x, def f of x, and then you have that indentation. Anytime you put a colon at the end of a line, it assumes that you're going to be making another line and that this is part of some sort of a function or some sort of code that will, here, I'm just going to move this here, put another enter there. Yeah, so that we have this, let's go over one. And so I'm going to write just a simple function, but in a bit, we're going to let you pick functions, but here's my function, return. And I just picked this one because it was the one that I was experimenting with, minus 0.5. So that's the function, sine of x plus x minus 0.5. So you probably can imagine what this looks like. You know what sine of x looks like. It's a nice sine curve. You know what happens if you take sine of x and you add x to it. The sine curve goes up, and then we subtract off 0.5. So you take that sine curve that's going up and you slide it down a little bit. So I thought that would make it sufficiently complicated that it would be difficult to solve this using our normal analytic methods, but it's super easy to solve using the bisection method or any other method. Okay, so once you have this return, you need to go back, like move the cursor back over so that it's on the left-hand side so there's no spaces. And then just to experiment, we could do this print f of whoops, f of, and you could pick a number. I don't care what number you pick. We could do f of 2 just for fun. And then we could do a control enter or press the little play button there, and you'll see that is f of 2. It's automatically, I believe everything is in radians. I guess we could find out pretty easily. F of 0, well, sine of, I'm pretty sure it's radians. So I don't know why they would do Python in degrees. That's ridiculous. Oh, can I just do pi? Is that a thing? Let's find out. Let's see, that would be sine of pi is 0 plus pi minus 0.5. Yeah, I think that's right. So 3.14159 minus 0.5 is 2.64159. Excellent. Okay, so I'm happy with this. So let's go to a new line of code, either pressing the plus code button at the top, or like I just did, press shift enter. And we'll define, so here's, like I said, I'm basically the program, what I'm looking to do is I want to have a bisection method. It's really easy. And then I've got the next one is Newton's method and the secant method. Those three, and then if we have time, we'll do the bracketed methods. But I just want to make sure that you see it's actually quite simple. And you know what? Newton's method is really the easiest of the bunch. Yeah, let's do Newton's method first. It's so easy. So Newton's method. So here's how we'll do this is, yeah, it's so short. It's surprising. So we're going to define a function, and this function is going to be Newton's underscore method. So you can call it whatever you want, but Newton's method, just because that's pretty descriptive. And then the input will be fp, which is going to be my f prime. And then, let's see, a and the tolerance. So just so you know, I probably should put some comments in here, but I'm being a little bit lazy today. F is the function I'm trying to solve. I want to solve f of x equals 0. Fp is the derivative of that function. We're going to have to go up there and define that in a minute. A is your initial guess, so you pick your initial guess, and the tolerance, how close do you want to be to the truth? So there's your thing. Put a colon at the end, hit enter, and it should automatically indent. Okay, so now we just have to remember what is Newton's method. So Newton's method says that you're going to define sort of this function specifically. Here, I'll just call it B for now. We'll come back to this, but this next guess, I'm trying to figure out why can't I, just a minute. Oh, there we go. Sorry, I was trying to, there we go. I don't know why I have an extra thing up there. It doesn't matter. Okay, so I just want to type in the formula, the Newton's method formula. So this should be somewhat familiar to you. So the next term is going to be the previous term. So A is the original term. So it's the previous term minus the function value evaluated at that point divided by the derivative evaluated at that point. It's that simple. So Newton's method, it takes that point, it shoots a line down, well, this direction, down, well, I don't know, it could be either way, finds where that crosses the x-axis, and it's like, that's my next guess. And then it does the same thing, gets it, and eventually finds the truth. So there's that line, and then just because it'll be better, because I don't want to mess with the little a, I'm going to say a is equal to little a. You'll see why in just a minute. Okay, so there's my function. And now I'm going to repeat what I just did over and over again until I'm close enough. Oh no, why is it disconnected? Well, I don't know. Well, anyway, so I'm going to keep doing this. So while what? While ABS, the absolute value of B minus A, is greater than the tolerance. So that's what we're going to do, is while this is greater than the tolerance, then you're going to just repeat what we just did. So you're going to see that I'm just basically going to copy these two lines. So give me a second here. So I'm going to put them in there. And actually what I'll do is, in order to preserve the letters, so that basically I don't want to overwrite B until I'm done with it. So I'll do this. So just to explain, I'll get to this in a sec, but so I make a new letter, a new variable. C is going to be the B that I computed before. So you have your original guess, which is A. Second guess is B. And then this is the third guess, which is C, which is B, basically putting B into that formula there. Just Newton's method formula. And then I have to sort of swap some variables. So A is going to equal B, and B is going to equal C. And the reason for this is so that when it loops around, it goes back and it says, okay, how close am I? Am I close enough? Yes or no? And then if not, let's run through this again, and we keep going. I probably should have an additional thing to guard against this blowing up, like some sort of a limit to the number of iterations I do. I'm not going to worry about that right now. Maybe I can fix it for Wednesday. But for now, I just thought, let's get these on the board. That's pretty much it. We're done. Well, almost done. So you'll need to back off one level. So I don't know if you can see what just happened there. I've moved my cursor back one level so that it's on the same level as the while statement. And I type return C, and that's pretty much it. So that's my Newton's method. See how simple it was? Now, I know this isn't the most robust code because, like I said, if we're following some sort of an asymptote going off to infinity, this isn't going to pick up on that, which, I haven't got any guards against that, so I might get some sort of overflow error. But it does the job. It does Newton's method as long as it will converge. So let's test it out. So what we'll do is we'll print, let's see, Newton. By the way, whenever you're typing, it's a little bit annoying, all this junk here, but when you're typing, whenever this comes up and it says, hey, I think I know what you're going to, now this isn't really AI. Most code like editors will do this for you. I love it because then you don't have to type anymore. Once you see this, just hit tab and then it'll fill it in for you. Okay, open parenthesis, there it is. So yeah, I don't know why it's showing, I might figure out how to shut off all that nonsense as well. But now we'll type in F prime. My initial guess, I guess we could start with either 2 or 1. We'll do 2. I don't know that it matters. I guess we'll find out. And then let's go with 0.0001 as the tolerance. And that should do it. Now, there is one thing that is lacking from all of my code here, and you can't really see because you'd have to zoom out to see it, but you probably see it in your code, and that is I never defined F prime, FP. So see, that's even Colab knows. It's like, hey, that never got defined. So I got to go back up here. So bear with me for just a minute and go up. So let's see, can I just hit enter? Yeah, there it is. Where is my mouse? Sorry, I have 2 screens. I can't see one. Okay, so there it is. So back here, when I defined the original function, I'm just going to also define the derivative. So put the derivative in here, FP. And here, even though there is a package called SymPy, so there is a package that we could load that would allow us to actually do the derivative. We don't need it because you all know how to do the derivative. So we'll just type this in. We could play with SymPy later. Right now, let's just do this. You know the derivative of sine is cosine. You know the derivative of x is 1. You know the derivative of 0.5 is 0. So there it is. And I guess we could test this out. You could just do this. FP of pi, little pi. Yeah, so just to make sure that we've got it all coded properly, and then control enter so that I can see. There it is. So apparently, yeah, that makes sense, that the derivative, so if I were to plug pi into this, cosine of pi is -1, plus 1 is 0. And that was, we determined that was correct earlier. So everyone okay? Okay, let's see. We're moving on. Okay, so let's go back down here and let's see how it works. Notice that that little orange squiggly line is gone. So now you can control enter up here. Make sure you did, in fact, it's not good enough to just type the code in for FP up top. You actually have to run that code so that it'll be in the memory. So you probably know this already. I just want to cover all my bases in case anyone is like, I've never done Python or whatever, or not, I'm sure some of you haven't done Python, but like never programmed. So anyway, so let's control enter this, and there it is. Whoop-dee-doo, right? Not very, it's like, there it is. That is the approximate solution, by the way, to this. One of the things that would be nice, and this would be helpful, at least for me, as I try to, understand what's going on, is to understand what's happening back here. So what I mean by that is I'd kind of like to know what happened in this loop. How many times did it go through this loop? That sort of thing. And so to figure that out, what I'm going to do is I'm going to add two print statements. One of them is back here. I'm just going to type print. And what I'm going to print is just A. Now, this is not going to be very exciting at all because you already know what A is. You put it in there, right? That was part of your input. It's right up here. The other thing is I'm going to write here, right after the while statement, I'm going to print B. So what this is going to allow me to do is it'll allow me to at least visually see all of the guesses that came, like, so A was the first guess, B is the second guess, and then as we go through this loop over and over again, we'll see the third, the fourth, the fifth, and the very last guess will be the one that gets returned. So let's see what happens when we put that print statement in there. Control enter, and where is it? It's down here. Ooh, interesting. Oh, that's so exciting. Sorry, I didn't realize. I had experimented with a different input earlier. Wow. Okay, just so you know, earlier today I was experimenting with 1 here instead of 2. And if you put 1, it's nowhere near as exciting. So if you do this, it's like, well, you go right to it's like 3 iterations. There's no, this 2 is much more exciting, apparently because 2, here, let's see, let's do that again. Yeah, so 2 must be on one of those humps. First of all, it's like, well, let's go way back here to -2. And then it's like another hump that shoots it way up to 5 and then to 2 and then to -19. It's going all over. Look, 169. And then, but eventually, I'm encouraged that eventually it gets back. Anytime you have humps like that on a function, Newton's method tends to do this sort of thing. It can wander back and forth. That's why we like bracketing. It's because bracketing prevents it from doing that sort of thing. So, but eventually it gets to the answer. So that's kind of cool. Maybe I should stick though with 1, just so that we can compare. That's what I did earlier, and it'll allow us to compare this method with the other methods. So there's Newton's method. So any questions about Newton's method? Is there anything you have that you're like, I don't know why we did that? I mean, it's pretty straightforward, but maybe you're not sure about something here, like why we did such and such. All right, so let's take a look at secant. Sorry. So secant method. Secant method is almost the same as Newton's method, so that's why it kind of makes sense. I know we're going backwards, but I think it's good. So what I'm going to do, because secant is almost the same as Newton, I'm just going to copy this entire block. Does that do it? Yeah, there. So I just Control C, copy that, and I need to Shift Enter. Okay, and then I'll paste it down here. So basically, I think there's probably somewhere I could have clicked and copied the block, but whatever. And then I'll just change this to match the secant method. So instead of Newton's method, I have the secant method. And the secant method, just to remind you, you start off with 2 guesses, and then it takes those guesses, it makes a secant line, connects the dots, finds a new point, and then it connects the dots from that point and one of the 2 previous points and finds the next one. So each time it just takes the 2 previous points and finds the next one. So we need 2 points, and then we'll find the third. So let's see. So the differences are right here. So the B, let's see if I can get this right. Oh, I see what I did there. I just did that because there's no sense in, here, let's escape. There's no sense in having an initial iteration, if you will, because, so I'm going to have A, B, and C. C will be the new thing. It'll be almost this, it'll look very similar to what we just had. So same thing, while the absolute value of B minus A is greater than the tolerance, we're going to print B just to keep track. Here's where this is the big difference right here, is instead of the FP, we're no longer using the slope. Instead, we're going to use the divided difference, the secant line, as an approximation of the slope. And so I don't know how, I'm going to just do it this way because I like doing it this way. So, so we have f of B minus f of A, difference in the y values, divided by B minus A, difference in the x values. So that is the definition of the slope. So this looks a little different than what we had on the PowerPoint last week, when all the craziness with the hospital. And I mean, I was literally in, like, the nurse was like, wheeled my wife off, and she's like, you could go out in the other room if you want. And I'm like, can I just stay here? It's like a private room. And she's like, yeah, if you want to. I was like, good. So I'm doing my videos and whatever I could. So yeah, I didn't want to be out because I made a couple videos out in the main waiting room, and like I had to say, hey man, I'm going to make some videos for my class here. He's like, okay. And I'm there mumbling. Felt a little embarrassed, but not too much. Anyway, so this, it looks a little bit different because in the book they put the B minus A on top because they reciprocate because of this divide here, but it's the same. Anyway, that's it. That's the, oh, and we should also change this down here. So let's try this. Change this to secant method. And we're going to go, let's see, I guess we could use 2 and 1. Let's see if that works. It's not what I used on, let's see though. That'd be an interesting experiment. And yeah, I think it's all good, So let's do this, Control Enter. Oh yeah, okay, that worked. So here again, all that really matters is this answer here. But notice that we got to it eventually. And it took us a little bit more time, a few more iterations than it did when we did the Newton's method. So that's the idea, is we want to compare these so we can talk about convergence rates, and we aren't going to get too into the weeds with the big O and the convergence and all that. Okay, last one, and then if we have time, we're going to be able to do I think we are going to be able to do the bracketing. So, any issues with secant? Wow, you guys are just so compliant, or maybe you're just like, well, if we don't talk, then we get to go get our lunch quicker, or whatever it is. Okay, final one is bisection, and then once we have these 3, the bracketing is simple. Okay, so bisection is the one that's different from the other 2. So let's see, we're gonna have to start from scratch. Def bisect, let's see, what did I call it? Bisection underscore method. And then the inputs are going to be F, A, B, and the tolerance. So that's so just to explain, we have the two sides of the interval, and then the tolerance is how close we want to get. Okay, so first, oh, forgot my colon. Don't forget the colon. First things first, I am actually going to check this. If F of A times F of B is greater than 0, or F of A, I don't care. Let's just go with that. So if F of A times F of B is greater than 0, in other words, if the function values are both on the same side of the x-axis, either both positive or both negative, it means you aren't guaranteed that there's a root. So there's no sense in proceeding. So if that happens, then put a colon there. We're going to return, and I will make an error message, no root in the given. I suppose this isn't necessarily true, but close enough. Probably I should say something like input function values need to be on different sides of the x-axis. This is whatever. This is what I wrote earlier, so this is what I've written. I'm going to stick with it. Okay, so let's back off one. So that is just going to check to see, as long as these two things have function values on different sides of the x-axis, we're going to keep going. And so we need to be back here again in the same line as the if statement. Otherwise, it will just interpret whatever we type as being more of what we're doing if that thing happens. Okay, so now the rest of this is pretty straightforward. This probably isn't, well, yeah, the way I did it is a little cheesy, but I don't care. So I have the left, which is going to be the minimum of these two things. So whatever A and B are, the left is the minimum, the right will equal the maximum. And of course, you understand what I'm talking about, that if you have an interval, if it's between -1 and -3, the left is going to be -3 over here, the right will be -1. So it's whatever the two, it's just sorting things out. I don't know that it's that important, but I just felt like I should do that. And then now I have my while statement. So this will feel very similar to the other two methods. So while right minus left is greater than the tolerance. So tolerance meaning how close do we want to be to the truth? Don't forget the colon. Then we're going to do the middle. The middle is equal to the right plus the left over 2. And then we're going to print, oh, well, let's save that. And then we're going to say if, what did I say there? Oh, I see. So if the function value evaluated at the left times the function value of evaluated at the middle, if those are the same, if that's true, then what we're going to do is we're going to say that the left is now equal to the middle. So in other words, you know how it works, is that you've got these two that are on different sides of the x-axis, and then you find the middle, and if the middle is on the same side as the one on the left, then you're like, okay, this is my new left side. And if the middle is the same side as the right, then you're like, okay, that's the new right side of my interval. So as long as, if they're on the same side, then we make the left now the middle, and then just back off so that it's on the same level as the if there, and we're going to say else. So else just means, well, if that's not true, here's what you do. We make the right equal to the middle, and then that does it. This makes me nervous. Sorry. Well, I'm just worried about what if it equals 0? Well, what's that? Yeah, it'll be the else. Well, I know what I can do. I know what I can do to fix it, just to make myself feel better. It'll add more code. I'll fix it later. It's just like by dumb luck. Here's the thing, is by dumb luck, you might hit the root exactly. And if that happens, that could mess up this, because yeah, it's just, I'm worried. And if you do hit the root, then you got lucky. You should be able to say, hey, like you just stop. Like this is the root. There's no need to go further. So that's the only thing. But let's not worry about it for now. The example, you aren't gonna. I can put I don't want to complicate things. Okay, so we back off so that we're on the same level as while. If you see the while right above? So return, and we're going to return the middle. Now, I have the same issue with this as I had with the Newton's method, and that is that I would like to sort of keep track of all of the guesses, where are they going. And so what I'll do is up here, I'll just put just 3 print statements. Before the while loop, I'm going to put print left and print right, which honestly is kind of dumb. Well, I put it because those two are just the A and B. So it's really not going to be very surprising, but I kind of want to keep track of, well, there's 2 guesses. Technically, that's 2 guesses. And then inside my, my little code here, right after I compute it, I'm going to say print mid. So really, all I really need is the mid, the middle, but whatever. Very nice. Okay, so finally, let's actually test this. So bisection, there we go, bisection method. And then we're going to put the function is that function that I had up above. For the left and right, what did I use here? Just so I have the same thing. 0 and 1. 0, 1, and the same tolerance. Is it 3 zeros, I think? So do the same tolerance as before, just so that we can compare. Yeah, 0.001. And the reason I'm using 0 and 1 is because I know for sure that the root is in there. It's a little over a quarter is where the root is. So anyway, now that you've got that, let's see how long it takes. Oh, took quite a while. I mean, it's considerably longer in terms of number of guesses than the other methods. So this is the difference. When we made this, maybe not that big of a deal, but when we made a big deal about